In this video, I'm going to be doing the design of a particular Sensenich propeller, and I'm also going to be doing a flow simulation of that propeller. Now, all of the work is going to be done in Solidworks, both the design and the flow simulation. Now, I chose this particular propeller because we happen to have this propeller in our shop, which is actually a hangar full of aircraft that we have, and I wanted to create the model as accurately as I could. However, I only had the Sensenich repair manual. Now, in the repair manual, and by the way, I did not make these notations on the page, the repair manual gives you various indications of how far away from each other the stations are. Right here are the station positions, and what are the blade dimensions at various points at that station, and what the pitch or blade angle is at that station. But one of the things that this repair manual does not give you is the camber of the actual blade. And I made an assumption, and I mentioned this through the video, that that the camber of the blade is going to be the same throughout the length of the blade, which may not be completely true, but it's the best data that I had to go with. So with that said, I also had to measure that camber, but I couldn't do it directly because there were no indications as to that camber on the repair station. So what I had to do was I had to create a fiberglass model or a mold, right? You can see that here, right? This is just extra foam that was used to give stiffness to the mold. But here we have the mold that I made of a section of the propeller, and then what I was able to do was spray paint in here and get a really good idea of what that curve was like. So if I get rid of the mold, then you can see the dimensions of that mold really well. So after I was able to take some of those dimensions, I realized that I could, in fact, find the camber and find an airfoil which would match this mold on the Airfoil Tools website, which I'll go into later on in the video. So to proceed, I was able to make a spreadsheet, and that spreadsheet has all the information that I will then use in order to create the SolidWorks model and the SolidWorks flow simulation. So here, for instance, we have the station numbers. I've just arbitrarily named them, and the station position in millimeters. And they're, of course, progressive. Now, just to note, this row here called reference geometry, this is an artifact of how I actually built the propeller in SolidWorks, because you had one reference geometry or one prop station at this distance, and then this is the distance from that particular station. So I created reference geometries which were distances from each station. This would be in absolute terms, this would be in relative terms. This is the blade, the chord length at each station. This is the blade angle, and this is the blade thickness at each station. And I'll use that information all the way throughout the propeller design. Here we are at the airfoil plotter at Airfoil Tools, and what we are going to do is find our NACA 4418 airfoil. Hopefully you can do that quickly. And there we are. Now we have to give it all of the information that we'd like to give it. See, here's the shape of the airfoil, but we need to put in the proper chord length. So for this particular section, it will be 140.7 millimeters. The thickness is 100%, and the origin will be 50%, and they will all be 50% because we want to be able to twist these blades, or at least rotate them in the same direction. And the pitch for this particular one is 33.6 degrees. And you can see rotated about its 50% point, and we will now download the file. Okay, that's been downloaded. Now what we're going to do is we're going to do one more. Actually, there are 6 in total, but we're going to do one more right here. So we're going to say this particular chord is 143.2. Thickness in this case is going to be 70%. And the blade angle is going to be 28.3 degrees. And we've got our plot, and we're going to download that. What we see now is the directory where we have all of the files which we downloaded from the prop tools. And what we'd have to do now is we have to manipulate them so that Solidworks can import them. And we can see that what we'll have to do is open up a spreadsheet, and I have to add another column, but first let's get rid of some of the data that we don't need. So we'll delete this, shift the cells up, go down. We don't need the camber line data either. Delete that. What we'll do is insert a column and add our third dimension, which is, in this case, the station, which is going to be 289.5. Double click that. And now we have to make sure everything is in the proper format. So we'll go data, text to columns, next, space, next, and finish. And what we're going to do is save this as the type of file that SolidWorks can accept, which is the text file .txt. So we'll have to do that with all of the files, and we'll close that, and we'll do it with one more. And here it is. We'll delete these rows. Delete this data, which we don't need. Insert column. Add the Z coordinate data, which in this case is going to be 434.3 millimeters. Make sure that it's in the proper format. Finish. And do a save as. And there we are. In Solidworks, in order to create the correct station positions for the blade, what we're going to have to do is add separate reference geometries to the right plane. And we're going to do this now. So here's our first plane. And in our Excel spreadsheet, which I'm going to pass off to a different panel, so you can't see it, but I can. I'll be reading off of that. We can see that the first station is going to be 289.5 millimeters away from this station, so I want to make sure I'm in the right units. Okay, so your right plane, shift and drag, and we're going to put 289.5 millimeters. Of course, that's a bit far out there, so we get a better idea. And we can save some time by adding 4 reference geometries at the same time if they happen to be at the same spacing difference. I believe we have 144.8 millimeters, and I'm reading this off of the spreadsheet, and I'm going to put 4, and there we go. There's one more, which is at a different spacing. That is 96.5 millimeters. Hit OK for that. And we can see that these reference geometries will in fact represent the stations of the propeller, and we have data that represents these stations that comes from the Sensenich repair manual. What we need to do now is to import the curves which would represent the camber of our airfoils at the varying stations of the propeller blade. So I'm going to do insert, curve through XYZ points. We have to find it. We're only looking for text files. 33.6 degrees twist, that will be the first curve that we import, and that would be the curve closest to the propeller hub. Hit OK. Now, a curve is not necessarily a sketch in SolidWorks, so we're going to have to create a 3D sketch so that we can modify the curve. So now what we have to do is we have to take this curve, select it, and convert entities. Hit OK. Now we can modify that sketch. And we're going to have to, because as the curve comes in, you notice that it's incomplete. And drawing a loft, which is something that we're going to do later on, would not be possible with an incomplete curve. So we're going to select that, and we're going to close that with a tangent arc. There we go. So you can see that is a closed curve now. Don't actually need to see this plane. We haven't deleted the plane, but we just don't need to see it right now. So we're going to repeat that process with one more curve for the purpose of the demonstration. And we will use the next file, which is 28.3 degrees twist. Okay. And we're going to create a 3D sketch. Okay. And select that. Convert entities. Hit OK. Close that with a tangent arc. No, I have to select it first. And hit OK. And there are 4 more. I will do those off camera because the process is exactly the same. Here we can see that all 6 of the stations have a particular airfoil curve in them, that of the 4418. If we rotate this view, we can see that the propeller is going to have a twist. Now, I have to add the connection point from the blade to the hub of the propeller. This will be circular, and I needed to pick the right plane, which would be the right plane. From my physical measurements of the propeller, this circle sketch will be 76.2 millimeters. And hit OK. Isometric view. Now I'm ready to use the Lofted Boss feature of Solidworks to connect these individual sketches to form what will look like a blade. So we have the hub connection, and we can add all of the other sketches, which are the stations. Hit OK. There we are. We really don't need to see the individual curves now, so I'll just hide them. I won't delete them, we'll just hide them. Now we will add a small dome. If we can rotate it properly and get on that face, that should be enough. That's how big we'll make that, I'm not exactly sure. that's way too big. Just enough to close it off and show that we have something there other than a hard edge. Yeah, I think that'll do. What I have to do now is add the actual hub. So we'll zoom in on that. I'll have to add a sketch. In the front plane, and that will be circular. According to my measurements, that would be about 150 millimeters. Don't know what I did wrong here, but we'll fix it. Okay, and we have to set that a certain distance away from the prop itself, which, believe it or not, looks fairly close to where it should be. Let's change it, see if we can make it a little better. No, it's wrong direction. Well, that was probably about where it should have been in the first place. Hit OK. Let's look at that to see if we've got it in the right orientation, and we do. So now we have to add a feature and extrude that. Of course, I have to choose the correct plane. And we will choose this. Nope, that's not what I wanted to do. Feature, extrude. There it is. And it just happens that 40 millimeters was the last value I picked when I did an extrude, so that seems to be about right. We have to do that in 2 directions. So let's hit OK. No, I do not wish to do that. Thank you, Solidworks. Let's check this out. There we are. And the hub is included in the design. Now we'll create the remaining blade by using a circular pattern generator. Let's see, so there's an easier way to choose the features and faces. Eliminate that from here. Seems to work best. Hit OK. And there it is. The only thing remaining is to insert a dome If I can remember exactly where. Features, there it is. I'm going to show the preview. We don't want to make that too big. Let's call it good right there. And we have our working propeller. Pretty much to the dimensions of the Sensenich propeller. You can see that. Yeah, let's look at the twist. Now, of course, as I mentioned early on, these dimensions won't be exact to the propeller because I made one very big assumption, and that is that the camber of the propeller would remain the same throughout the length of the blade. That may or may not be true, but that was the best data that we could use. Let's create a flow simulation in Solidworks and get an idea of flow trajectories. What we'll have to do is go into that window and we'll use the wizard. Give it a name. We'll use these units and make things a little bit more convenient. External. And rotation. This is very useful because it gives us an idea of how this propeller will behave in a simulated environment of rotation. And our axis of rotation is going to be the z-axis, not the x-axis. And the speed of rotation, I think for this case, about 160, minus 160 radians per second, which works out to roughly 50, a little over 1500 RPM, but minus because of the direction of rotation, the direction that I've actually built this in. Change the z-axis here. And our gas will be air. And we'll ignore these for now. We'll accept this. And in the z direction, so we also have, besides rotation, we have a velocity in the z direction, as any prop would on a aircraft. So I'll say 150 miles per hour. And I think that's about all. We can use temperature and pressure as the default values. This is our computational domain, which looks good from here. You don't need to make it too big, don't need to make it too small, but we don't have to actually view the domain itself. So while it still exists, we will hide it. And let's add some goals to this. So what we really want to look at is pressure So we'll add this. Total pressure. Of course, we could add all of them, but the simulation would take pretty much forever. So we're really interested in velocity, especially in the z direction. I think that should be good. We'll use average y. And that should be sufficient to get us a decent simulation. Boundary conditions, probably fine for what we're doing. And these are all our actual goals, so the solver will have to solve for all of these conditions. And let's see what happens. I believe that should be it. Let's run the simulation. Now that the simulation is finished, let's see how we did. We've added a flow trajectory. Let's see the definition here. Just to repeat, I've added the faces for the flow trajectory analysis. We're going to be looking at velocity in the z direction, pretty much. I have pipes. And I can also change that to other view capabilities such as bands lined with arrows. Right now I just happen to have pipes. I've added, say, 100 points for visibility. And there we see. Not all that bad. Of course, the worst place is directly behind the hub. Let's see, maybe I can play an animation of that. Just for effect. There we go. Right out. Okay. So let's stop that. Let's hide it. Look at a surface plot. And this will give us an idea of the pressure gradient along the length of blade. There we are. What we can see here is a very constant pressure all the way down the length of the blade. And that implies that we have a constant angle of attack, or pretty much near constant. Just for fun, I did another simulation for a prop that I built from the same dimensions as the previous prop, but with absolutely no twist. Let me focus in on that, and you can see that there is no twist in the blade. So this prop simulated at the same rate as the previous simulation. See, there we go. Minus 150 radians per second, which is just over 1500 RPM, and 150 miles per hour. And results, not as good as the previous simulation. And let's do, yeah, you can see things are getting much more jumbled up here, and there's a lot more misdirection here and here. Let's hide that. Look at the surface plot, pressure gradient, and you can see that we don't have what would be considered a constant pressure gradient along the blade, probably implying that we wouldn't have a constant angle of attack throughout the length of the blade. And if you notice, a very high pressure gradient right at the tip here. And I should note that during the simulation, it was noted that it was giving me a warning that parts of this blade were in fact going supersonic.